Now, I mentioned earlier that water could be either an acid or a base. Now, that's a property known as being amphoteric. But in this particular case, we're showing that water, in the same reaction, water can be an acid or base. Or really what we're showing is that in any solution that has water in it, this is going on. The water molecules can dissociate, and when they do, not very often, but when they do, it's really important because, well, we can tell exactly how much. We know that in pure water, water that's at 25 degrees Celsius and doesn't have dissolved gases in it or anything like that, in pure water, that concentration of water molecules that dissociate is 1 times 10 to the negative 7, and they produce hydronium ions and hydroxide ions in that concentration. So for any aqueous solution, whether it's pure water or has sulfuric acid in it, that water dissociation relationship remains constant because it's a equilibrium system. And so the Kw is 1 times 10 to the negative 14, and you will need to remember that number. It will be so important to you. In any aqueous solution, the hydrogen ion concentration times the hydroxide ion concentration is 1 times 10 to the negative 14. Looking at this graphic, trying to decide what I'm going to say here. There are 4 concentration ways of expressing concentrations of hydroxide and hydrogen ions in acid and base solutions. And we're interested often in those 4 different ways of describing these concentrations, and they're all related and interrelated. And you can go back and forth between these. You can go back and forth between these. You can go back and forth between these. So if you have one, you can calculate the other 3. And in fact, if you have one of them, there's more than one way to calculate the others. So keep in mind that pH is the negative log of the hydrogen ion concentration, and we'll get you some chance to practice calculating that. And you need to just get really comfortable with knowing that when you put the numbers into your calculator, you are getting the right answer. The hydrogen ion concentration, if you need to calculate that, and you have pH, well, it's 10 raised to the negative pH, and many of your calculators have a analog button or something like that. You can do the same calculation for POH. If you have hydroxide ion concentration, you can calculate POH by taking the negative log of that hydroxide ion concentration. Or if you want to know the hydroxide ion concentration, you can find it by taking the negative log of the by taking 10 and raising it to the negative POH. So keep that in mind. Also keep in mind that pH and POH add together always to make 14. And that turns out to be true even in those cases where maybe pH is something like -1. Well, guess what POH has to be? Well, POH would have to be 15 because they have to add together to make 14. Keep that in mind. It's really useful to know. And also keep in mind that the hydroxide ion concentration times the hydrogen ion concentration always equals 1 times 10 to the negative 14, so you can convert back and forth. So There are some examples in your book. You can look at this, practice these on your calculator, look at the examples there in your textbook in section example 14.3. And here, I guess, is just another graphic that I wrote into these notes at some later time of the same thing I was just showing you earlier. And I actually think this one is organized a little bit better. So you may want to study it and see if it makes sense to you. That we can convert between pH and pOH using this. We can convert between hydroxide ion concentration and hydrogen ion concentration using these. And I guess I have left off going back and forth between these. So, but you can add those in and make sure you're able to do that. And I believe that example is in your textbook. Study it. Notice that when you're calculating the pH of strong acid solutions, the strong acid solution is equal to the concentration of the hydrogen ion because the reaction goes to completion, goes all the way to the right. So if you have a 1 molar HCl, you'll have 1 molar hydrogen ions and 1 molar chloride ions. So the pH is the negative log of 1, which in this case is 0. Well, always 0, but yeah. pH in that case was 0. Okay. So there are some further examples. I'm not going to take time to do them in this video. I'm going to ask that you go to that section of the textbook and study them a little more. And once again, you should know the common strong acids. Here are the 4 you're most likely to encounter. And keep in mind that for these strong acids, the hydrogen ion concentration of a strong acid is equal to the concentration of the acid because the equilibrium lies far to the right. But if you're calculating the pH of weak acid solutions, there are a series of steps you have to take to solve those kinds of problems, and you can look at those steps on page 637 and 638 in your textbook if you have Zumdahl's 7th edition. So I think we have time to go over this problem on this section of the video. So here's an example where we have a 0.1 molar solution of a weak acid, and we know the Ka from that table back on page 628, which you're going to refer to often. Now the majors, these are the steps that are described there in your textbook. And so the first thing we're going to do is look at the major species that are present. We might get hydrogen ions from the HOCl, and we might get hydrogen ions from water. Both of those things produce hydrogen ions, but which one is the stronger acid? Well, you'll notice that this acid, this Ka, is so much bigger than the Ka for water that that's the only thing that's going to put significant amounts of hydrogen ions into the solution. So that's what we're going to look at. So we're setting up that equilibrium system and the icebox for that equilibrium system. Here's the equilibrium expression for this system. So initially in our ice box, we have a 0.1 molar solution. We know the reaction is going to go somewhere to the right. So these x's are going to increase because there wasn't any of them before. And in our final solution at equilibrium, we'll have x for the concentration of these and 0.1 minus x for the concentration of the acid, because it's a weak acid. Not much of it's dissociating. In fact, so little of it's dissociating that it's this value of x is so small compared to 0.1 that we are going to ignore it, simplifying our problem to be x squared divided by 0.1 equals 3.5 times 10 to the negative 8. So if we multiply each side by 0.1 and take the square root of both sides, we get the value for x. And from that, we can calculate pH of 4.23. So study through that example, look at more questions in the book, and for goodness sakes, get some help if you're having a question on that. Yeah.